Alright, what I want to do is just work two more examples. Now these are going to look like mathematics examples, however, they're not going to be. They're just going to be mostly conceptual. We're going to do a little bit of math, but for the most part, these are conceptual. Do you understand what's going on in a circuit when we're charging and discharging a capacitor? Okay, so let's go ahead and look at the first one. This is example number 7 on the worksheet from my student's class. Alright, so we've got a diagram below. We're going to determine the charge on the capacitor and the current in the circuit at two different times. Now, before we try to answer this question, let's try to remember what happens. When we close the circuit, so we go close, right? Then the potential difference is going to cause a current to flow, right? And so you're going to get the same potential difference eventually, but the current's going to flow, and initially there's not going to be any charge here, right? It's not until the electrons start to flow and start to move around that the capacitor is going to get charged up. And no, over time, the capacitor is going to charge up to a point that its potential difference is the same as that of the battery. Okay, now when that happens, well, we'll get to that when it's time. So let's just start with A. So initially, when the switch is closed, the electrons start to flow. We go from this 12 volts to a potential of 0, right? That's why it's flowing, because there's 0 potential there. So it starts to move, it goes there, it'll continue to go as it charges up. Alright, so now what we need to say is, okay, first find the charge on the capacitor. Well, the charge on the capacitor, that's easy. It's 0 initially, right? When you close the circuit initially, there's no charge there. Because the electrons haven't gotten there yet. It takes time for the electrons to get there and start moving around and start charging up. And so initially, no charge. Okay. Now the second is the current in the circuit. Now the current in the circuit then, since this is essentially going to be a potential of 0, is going to depend on the potential difference that across your resistor. So that means that all 12 volts are going to be lost across the resistor. So we can just use our simple V equals R. This is as hard as the math is going to get right now. So 12 equals the current times the resistance of 14. And so when you do that, then you're going to just do 12 divided by 14, and you're going to get 0.857. So the current is 0.57 amps. Okay, so there you go. You got the charge on the capacitor, you got the current in the circuit. That's all it's asking for. Okay, letter B. Now this is after a long time. So the current's been flowing and flowing and flowing and flowing and flowing and flowing and flowing. And so eventually the capacitor is going to charge up. We're going to get a potential there of 12 volts across that capacitor. Now the energy is completely stored up. Now if this is 12 volts and this is 12 volts, you'll remember that our battery is plus and minus there. So the capacitor is going to be plus and minus, right? Because you're having electrons that are flowing to the positive, making this positive, and then you're going to have electrons flowing from the negative, which is going to make that negative. And so essentially you're going to have the same potential difference on your capacitor that you have across the battery. Now if those are the same, that means that the resistance doesn't matter, because there's not going to be any more electrons flowing. There's no need for the electron to go from 12 volts to 12 volts, right? The potential difference is the same. You've had the same potential on each side, and so it's not, therefore no longer necessary to have a current. If you want to look at it in terms of Kirchhoff's, right, as we go from the negative to the plus, as we go this way, then we're going to get a positive 12 volts. We go through the resistor, so minus IR, and then we go through the capacitor going from the plus to the minus, so that would be minus 12 volts equals 0, plus 12 volts minus 12 volts, so therefore IR equals 0. Again, you get that the current is 0 because it no longer needs to flow. Alright, now the second is, what is the charge on the capacitor? So again, straightforward, simple math. We know that a capacitor is equal to the charge over the voltage. So the voltage on the capacitor, the voltage difference is 12 volts. The capacitance is 5 microfarads. So Q over 12. 12 times 5 would then be 60. And this is charge, so microcoulombs. There you go. That's number 7. Let's go on and look at number 8. Okay, again, it looks like we got a bunch of numbers. It looks like we're going to have some math, but in reality, just like that last one, we're going to have a couple of very simple math things, and the rest of it's just going to be very conceptual. Okay, now this first one we're going to need to use a little bit of math for. We have essentially 3 switches. You got 2 resistors, 4 ohms and 6 ohms. You got a battery of 30 volts, and then a capacitor that is starting uncharged. Okay, So it tells us that initially the capacitor is uncharged, all switches are open. So now switch 1 is closed and switch 2 is closed. Now the capacitor doesn't even matter because that's not part of a complete circuit. So you're just going to have something like this where the current is flowing, and then we're just going to say, okay, now we need to calculate the current through R1 and R2. So the current has to be the same everywhere, right? There's only one way for it to go. Everything that it goes in has got to come out. So in this case, we're going to use V equals IR. We know that resistance in series, you just add them together, and so that's going to be 30 for the battery equals the current times the resistance of 10, because you've got 10 total ohms, and so the current is going to be 3 amps. Okay, so there you go. That's the first part. Now, switch 2 is opened and 3 is closed. So let's go ahead and open 2. Not going to let me erase, so there we go. So close 3, open 2. There we go. Wonderful. Okay, so now the current's going to be going through that, right? So plus, minus, so the current's going to go like this, just like that. Okay. Now, obviously, the current is not going through the capacitor, right? We mentioned that in class, that it actually doesn't flow. But because you have a positive potential here, it's going to go to the 0 there, and the negative potential here is going to go to the 0 there. And so, right, you're going to have negatives, electrons going this way. So electrons going that way mean current going that way. And then here you're going to have electrons going to the positive, which means current going that way as well. And so we can kind of show the current going that way, even though we understand that it's not passing through the capacitor itself. Alright, so now it says calculate the currents through R1 and R2 and the charge on the capacitor immediately after the switch is closed. Well, initially there was no charge, so immediately after closing, the charge on the capacitor is still going to be 0, right? It doesn't get charged until the electrons start getting there and moving around and getting it to charge up. So that instant when S3 is closed, it's still 0. Right? We know that this resistor is no longer part of the circuit, right? The current is all going around the outside. There's no reason for it to go through the middle. And so therefore, you could kind of treat that open switch as an infinite resistor, and an infinite resistor means that you don't need any current. And so therefore, the current through R2 is also going to be 0. And therefore, we can solve for the current through R1. So V equals I. You get to do a little bit of math. 30 equals the current times the resistor, which is 6. And so the current is 5 amps. Okay, easy enough. Let's look at C. Calculate the currents through R1 and R2 and charge on capacitor C a long time after the switch is closed. So the switch has been closed, the electrons have been going, and we charge up the capacitor. So eventually the capacitor is charged up until it's 30 volts. Right? If it's not 30 volts, if it doesn't have potential difference of 30 volts, the electrons are going to keep going. And so they're just going to keep going and going and going until a long time later, it's charged up with a potential difference of 30 volts, which means that then there no longer needs to be current through R1, right? If these are the same, electrons don't need to flow, and so there's no more flow going through R1. R2 is still the same. There's no reason for the current to go through there because it's not part of the complete circuit. And then the third part of the question, charge on capacitor C. Well, now you get to do a little bit of math. Yeah, C equals Q over math. This can be a tough one. All right, so C is 25 microfarads, which will equal the charge over the potential difference. So there you go, 30 times 25. And oops, I didn't get the 30 on there, so I'll just multiply by 10. So 750. So Q equals 750 microcoulombs. Oh no, I'm going into F. That's okay. We'll work it out later. All right, on to D. Sketch the current versus time graph R1 over a long period of time after S2 is closed. Well, we know that we start with a certain amount of current. We have that number up there. It doesn't really matter. We just start with some current, and then after a long time, we end up having 0 current. So now the question is, does it go straight down or does it curve? Well, that is going to depend on the rate of change of the current. If the current is always changing at the same rate, then it'll be a straight line. If the current is changing at different rates depending on how many electrons there are, then it's going to be a curve. Now the reality of it is that when we look at what's happening, right, as you get more charge here, right, as you start to get some plus and minus there, the current is going to have a harder and harder time flowing, right? If you've got some electrons here already, these guys don't really want to go there anymore, right? They still do because there's a potential difference, but there's less of a potential difference, and so there's less desire from those electrons. Yeah, they really, really want stuff to try to get there. And so kind of thinking of it that way, the change of the current is going to be less and less and less. And so because of that, this graph is going to then look like this. It's going to be a curve down to there. Now, in reality, it should get closer and closer and closer without ever touching, right? It's an asymptote. But, you know, you get far enough and you say, okay, well, a long time later, enough of the electrons have moved that there's essentially no more electrons moving. That current's small enough that it's negligible, right? So let's go, after D, can't forget, I put this down. A long time after the switch S3 is closed, switch 1 is opened and 2 is closed. So, oops. So now, a long time after this, it says that we're going to open 1. I didn't mean to do that. And close 2. There we go. Okay, so it erased that, but we didn't open that one. So now the current is just going to be able to go through there. See, we've already put the charges on our capacitor, which means it's now going to be the current's going to flow in this direction from the plus to the minus, right? So now calculate the currents through R1 and R2 immediately after switch 2 is closed. Well, R1 is no longer part of the circuit, so the current of R1 is going to be 0 because only R2 is part of the current and our circuit. So if we want now to do that, we're going to use our little bit of math, V equals IR. So now we have a potential of 30. We know that it's going to go up to 30 until you disconnect it from the battery, because when it's going to load up to the same potential, we talked about that before. And so now the current and the resistance, the only resistor there is now at 4 ohms, so 30 divided by 4, which happens to be 7.5. And that's going to be amps. Sorry, not micro. So just amps, right? 4 ohms, 30 volts, no micros. Okay, go on to F. Calculate the currents through R1 and R2 and charge C a long time after switch 2 is closed. So a long time later, right, the electrons are going to go and go and go and go and go. The current is going to flow and flow and flow and flow and flow. You could probably make some type of rap song about that. Go and go and flow and flow. Oh yeah, whatever. Okay, that's why I'm a teacher, not a rapper. After that, right, there's no longer going to be any charge because all the electrons are going to balance out. So we know that the charge is going to be 0 coulombs. Once that's happened, there's no longer a potential difference. There's no need for the electrons to flow. If they don't need to flow, they won't. Electrons are lazy. They're just like second semester seniors. They're not going to do anything unless they have to. So, just kidding. So now we've got resistance 2, the current there is going to be 0, and then we've got the resistance in 3, which is also going to be 0, and so we're done with that question. And so the last question again is sketch the current versus time graph over a long period of time. Similar things going to happen. We're going to have a lot of current to start with, and then it's going to decrease as an inverse until it gets down to 0 a long time later. Alright, so there you go. That's examples 7 and 8. I hope that makes sense conceptually as well as mathematically. And if not, feel free to ask.